What's up, class? Let's get into chapter 2.2, fitting lines to data points. So the first thing we're going to look at is what are first differences. So first differences are really just almost exactly what the name says. It's the difference, the first time you take the difference between everything within your X's and Y's. So here we've got year and we've got retirement plan. So the first difference between the 40,950 and the 42,900 is 1,950. If I take the first difference of the next set of numbers, it's also 1,950. The first difference of the next is 1,950, and the first difference of the next is also 1,950. Now, it's important to know that the first differences do need to be the same in order for it to be a line on both. So the first difference here is a 1. First difference here, also a 1. First difference here, also a 1. And first difference here, also a 1. So you can see as we go up by 1s, the first difference on this also goes up constantly by 1,950. Now, if you wind up doing a jump, so if you go up by 1 here and go up by 2 here, you should expect this to not go up by 1950. It should go up by 2 times 1950. So if you don't stay consistent here, it should at least go up by the same factor on the second one. But most of the time you want to go up consistent on both. Okay, so if the first difference of the data output are constant for uniform inputs, so this is our uniform input. Our year is a uniform input here, 21, 22, 23, 24, 25. The rate of change is constant, and a linear function can be found that fits the data exactly. So we can find a line that fits this data exactly. It fits it perfectly. If the first differences are nearly constant, a linear function can be found to approximate the fit for the data. So even if it's not perfect here, so say if this was 1950 and that was 1949 and this one was 1953 and that one was 1959, we wouldn't be able to find a perfect straight line to fit that, but we would be able to find a line to approximate it. So that's essentially what we do in this. So in the table above, can a linear equation be found to fit, approximately fit, or not fit the data? In the table above, right here, we can find one that actually fits it. So what you would need to do is either highlight or circle that. We can actually find one to fit perfectly. Okay, no need to approximate at all. Alright, so what we can do, if you wanted to find it by hand, let's scroll back up. If you wanted to find a data point or a line to fit this by hand, alright, so what I can do is I can say, okay, obviously every time I go up by 1, so if year is your X, retirement plan is your Y. Okay, so a rise in X of 1 causes a rise in Y of 1,950. So your slope is going to be 1950. So it's looking like Y equals 1950 X plus B. Now if you wanted to find B, you just have to plug in one of these points. You could plug in 21 and 40,950. You could plug in 22 for X and 42,900, and you solve for your B. We've done that a few times. You should be able to do that. Okay. Now, so what I'm going to do, instead of doing that, you can do that on the side. You can figure out what that B is by hand. Be my guest, please do that. But what I'm going to do next is show you how to find it on the calculator. So what you're going to need is you're going to need to have this list here, the 21, 22, 23, 24, 25, and the 40,950, 42,900, so on and so forth. You need to have that so that we can put it in our calculator. So let me bring up the calculator real quick. Alright guys, so if you're at your TI-84 calculator, here's what you need to do in order to find the equation of this line without having to do any hands-on work. So, first thing you're going to do is hit stat. Okay, Then you're going to go edit, hit enter. Okay, what it's going to do is going to bring up your list. Okay, so what we want is we want our X or in list 1, or in this case year in list 1. Okay, and then we want our retirement prices or payment in list 2. I've already typed the retirement payments in list 2. Now in list 1, what we're going to have is we're going to have 21 through 25. Now if you don't have these lists on your calculator, for some reason list 1 is completely deleted, you'll have to reset your calculator. There's tutorials all over YouTube on how to reset your calculator. It's a pretty simple process. So if you reset your calculator, your list will come back. There's no other way that I know to get it back other than resetting your calculator if you've deleted the entire list. But we'll start with 21. Once you type the first one in, hit enter. Type the next one in, hit enter. So on and so forth. Okay, you should obviously have 2 even lists. So our years were from 21 to 25, and then our retirement rate or whatever was here. So we've got all those typed in. Now we still need to find an estimation of the line here. So the next thing we're going to do is we're going to hit stat. We're going to hit calc. We're going to scroll down here to number 4. Linear regression is what this stands for. And what it does is it finds a line to fit it. Okay, so you should already have L1 in list and your X list. In your Y list it should be L2. Leave frequency completely blank. Now here's what I do recommend. I recommend that you store the regression equation in your Y1. To do that, you'll hit vars. You'll scroll right to Y vars and function. You'll hit enter. And then Y1 is selected. Hit enter. So you'll wind up storing your equation in Y1. And you'll see exactly what I mean by that in here in just a second. So we hit calculate. And what it does is it creates this line for us. So that our equation here is y equals ax plus b, where a is 1950 and b here is actually 0. So if you calculated it by hand, the b you should have wound up with is a 0. Okay. Now, since we're at the calculator, let me go ahead and show you this. If you go to y equals here, you should see that it inputs this equation here. So your equation is y1 equals 1950x plus 0. Now if you wanted to see it plotted with your points to see how well it fits your line, what you can do is you need to make sure your plot's turned on. So we'll go second, y equals, and we'll need to turn this first plot on. Okay, so we will go and turn it on. Make sure the one right here is selected, the very first one, which is the scatter plot. List 1 should be under X list, list 2 should be under Y list. You can change your marks to whatever you want to. If you want it to look a little different, you can change your color. None of that really matters. Okay, once you have it on, what you can do is you hit the zoom button. Okay, and then you're going to zoom down or scroll down to zoom stat. What zoom stat does is it graphs it perfectly for the scatter plot. Okay, if you hit enter on it, it shows your scatter plot of the points that you inputted in your XY list. Okay, and then it shows the estimation of the line going through them. As you can tell, this line fits these points perfectly. Okay, so not only can your calculator find your line for you, it can show you a graph of the line and how well it fits the points. Okay, so now let's get back to your lecture notes. Alright, so like I said here, if you found it by hand, you should have found that your B was 0, and it matches what we found with the calculator, so that your equation here is simply 1950x. Much easier to find it on the calculator than by hand most of the time. Alright, so if we move on, this example says table 2.4 gives the projected population in millions of females under the age of 18 projected for the years 2020 through 2060. Okay, so what you have here are the years and the population in millions. Okay, part A says draw a scatter plot of the data with the x value of each point representing the number of years after 2000. Now that's important here. So this after 2000 is very important. So our x here, when it says after 2000, instead of typing the year 2020 in, what we'll actually wind up typing in is 20 for year 20, 25 for year 25, okay, 30 for year 30, 30 for 35, 40 for 40, and so on and so forth. Okay, so for this one it'll be 45, 50, 55, 60. Okay. Alright, and the Y value representing the population of females under the age of 18 in millions. Okay, so this is essentially our X for our year, our population is our Y. If you need to write that, be my guest. So that's your X. Remember, this is your Y. Okay, so we can draw the scatter plot on the calculator. I'll go ahead and read through part B. B says graph the equation, and it gives you an equation to graph. And C says find the linear equation of best fit for the data using the calculator. So I'm going to do all three of these while we're looking at the calculator. You obviously should have your notes next to you so you can look at the notes and compare to what I'm doing on the calculator at the same time. But I can only show you one at the same time on my screen. So I wanted to go ahead and read A through C. So let's jump back over here to the calculator real quick, get this done. Alright, so we're over here at the calculator. First thing we're going to do is hit the stat button. And we're going to edit. And I've already got the list typed in. No need for you to sit here and watch me type all the numbers in for the list. The biggest thing when you're typing in the list, remember, you got to do the 20, 25, 30 because we're starting from year 2000. So year 2020 is 20 years after 2000. Make sure you get everything typed in correctly. If you don't type it in correctly, you're not going to get the right line and you're not going to have the right answer. So, if you're having trouble typing these in, go back and watch how I did it the first time. The only thing that I'll tell you that might help you is if you have all this information in your list, so say you had another list here, instead of having to go back and individually delete each one of those out, the easiest thing to do, go up to the top, highlight the list, hit clear, and then hit enter, and it clears the whole list for you. So if you need to clear out that old list, that's the easiest way to do it. Alright, so we got our list typed in here. We want to look at the scatter plot of it. So I'm going to do stat calc. I'm getting ahead of myself here. We want to look at the scatter plot. So what I'm going to do, I've also already got that equation typed in for B to go ahead and get it out the way. But if I want to look at the scatter plot, I'm going to go zoom stat, which is number 9. Okay. Now here's the scatter plot. So this is part A. The blue dots are part A, the scatter plot, right? So it's a pretty straight line. It's not perfect. I'm not going to be able to find a perfectly straight line that's going to fit all these points because it looks like it kind of curves here and then comes back up a little bit. Now, like I said, for part B, if you type in this equation 0.1x plus 36 and comment on how well it fits, if I'm looking at this, to me, it doesn't look like that line fits those points very well at all. So it doesn't look like a very good fit. Okay. Now, if we want to find the best fit line, what we're going to do is we're going to hit that stat, calc, and then we're going to do a linear regression. Okay, just like we did before. I'm going to store the equation in y1. Remember to do that, we go vars, y bars, function, y1, and we calculate. Okay, so our equation for this line is y equals 0.1555x plus 34.277777 repeat. Okay, now if I look at this on the graph, you could tell that this blue line, which is that linear approximation we just did right here, is a much better fit than that line they gave us in part B. Okay, so the calculator did an excellent job of finding it. Now you know it's not perfect, it doesn't hit every point exactly, but that's because those points aren't in a straight line. Okay, but it does a very good job of approximating those points. The red line, not so much. Alright, back to the notes. Alright, so if we're back at it and you want to write something down with me, it says graph the equation on the same axis we did that. Is this a good fit for the data? I would simply say no. Alright, C says find the linear equation for the best fit for the data using the calculator. We did that. Remember it was, what was it? It was y equals It was y equals 0.155x plus, and our B here was 34.28. Alright, so that's it. Now, the best fit line is the line for which the sum of squares of vertical distances from the data points of the line is a minimum. Okay. Now, we're not going to do that by hand, but the calculator does it all for you. Okay. We're not going to go find the squares of each of the distances and make sure that it's a minimum by hand. That's not what this class is about. We're going to use technology in order to do that. So, in order to find the best fit line, we use a process called linear regression. Okay. So this kind of explains how it works. Okay, we enter the data into the list of the graphing utility, which is what we've done. We create the scatter plot to see whether our linear model is even reasonable. So just like we did here, we did that. You can go about trying to change your Y max and Y min however you want to, but honestly the best thing to do is to use zoom stat. It does it really easy for you. Okay. So this is the exact same example we did here. Okay, it's just how it reported it in the book. Okay, and you'll see that we had the same results they had with the same exact line that they wound up with. Easy enough. Okay. Now, the next example says table 2.6 shows the median weekly earnings of women and men in 2013 in dollars. Let X represent the earnings for females. Let Y represent the earning for males. Let's create a scatter plot of the data. B says create a linear model that expresses male weekly earnings as a function of female weekly earnings. C says graph the linear function and the data points on the same graph and discuss how well the function models the data. Okay, so what we should know from this is we are letting X represent females. We are letting Y represent males. Okay, I'm going to type this in. Okay, we've got this table 2.6 right here. We're going to type this directly into our list like we've done already. We're going to create this linear model, and then we're going to graph it, and the data points on the same graph, and talk about how well it actually models and fits that data. So let's go over here to the calculator, get all this typed in, and then find the line and graph it. And I'll come back here and I'll write the equation down after we're done with that as well. Alright, so I'm over here at the calculator. If you don't remember, I'm going to go through it a few more times. Stat, edit, here's your list. I've already typed them in, remember? Our X is our women, our Y is our men. So your list should look just like this, okay? If you have trouble getting rid of and deleting out of the list, remember all you have to do is go up here, hit clear, hit enter, it clears out the whole list for you, okay? Alright, so now what we need to do, I'm going to go ahead and create the line for it. A lot of times what I like to do is go to Y equals, make sure everything's clear in here first. Then I'm going to hit stat, calc, scroll down to linear regression. Here, number 4. You can use number 8 if you want to. It just gives you, it does the linear regression, gives you the same line. As you can tell, the formula is just switched. It's not a really big difference or change. But usually I just stick with 4. Okay. So you're going to come down here. I'm going to store it in Y1. So vars, Y vars, function, Y1. Calculate it out. Okay. Finds the line for you. The line here is Y equals 1.46x plus negative 140.33 approximately. Okay. Now, it's in your Y1 here. No big deal. If I go over here to my graph, what I'm going to want to do is hit zoom, stat. Okay. That's going to readjust it for this particular set of data points. As you can see, the line is the best estimate for this. Now, it's a pretty good estimate of most points. It is kind of far off from 2 of them here in the middle, but I really don't think it does a bad job here. I think it does a decent job estimating these points here as far as a line goes. Obviously, it's the best fit line, so you're not going to draw a straight line that does any better of a job than this. You might be able to find a curve that does, though. You might be able to find a curved line that hits all these points. So, how well does it fit? For a line, it fits pretty dang good. You're right around, let's see, 5 points you're really close to, 2 points you're not. That's a pretty good fit. Okay, so let's go back to the worksheet or the notes. Let's write down the line and do a quote on how well it fits. Alright, so here we are right back at it. Filling this in, we already did A, did the scatter plot, created the best fit line. We had the equation y equals 1.46x minus 140.33. We graphed them on the same data point, or on the same graph, and we discussed how well it fit the model. We said it fits okay. Not the best fit, it's not a perfect fit, it's an approximate fit, right? Alright, so if we scroll down to page 4, I believe we've got another example here. It says the total U.S. population for selected years beginning in 1960 and projected to 2050 is shown in table 2.7 with the population given in millions. Align the data to represent the number of years after 1960 and draw a scatter plot of the data. Create the linear equation that is the best fit for these data where y is in millions and x is the number of years after 1960. Okay, so it's pretty simple. It's the same process we've been doing. The biggest thing here, 1960 is year 0, which means 65 is year 5, which is 70 is year 10, 75 is 15, 80 is 20, 85 is 25, 90 is 30, which means that 95 is 35, 98 is 38. Now this one doesn't stay consistent, and they don't have to stay consistent and go up by 5 every time, so keep that in mind. Which means that 2000 is actually 40. 2003 would be 43. 2025 would actually be, what, 65? And 2050 would actually be year 90. So here, it started out consistent every 5 years, but it changed, which isn't a big deal. You just have to keep track of that. So what we'll do is we'll put this in list 1, we'll put the population in millions in list 2. Okay, that's all I'm going to go over here and do on the calculator. So follow me on over to the calculator, we'll get that done. Alright, so we're over here at the calculator. Remember to get to your list. We're going to go Stat, Edit, and you're right here at your list. Now I've already got mine typed in, obviously. Remember that we're starting with 0, 0 and moving up, and it's not consistent. So don't get stuck in that up by 5 pattern, because it did change for this one. Alright, now what you'll also notice is that when you type in these numbers, it's going to wind up estimating them. Your whole number's still in here, like this last one. It estimates it to 408.7. That's because it can only fit so much within this little bound. Alright, so what it did is it rounded up with this last digit, which caused a 9 to round up, which made this a 7. Right? Your whole number's still here. It can only show so much of it here, so don't think that you're necessarily typing it in wrong. Make sure you're not typing it in wrong, but don't think that just because it rounded it, you did something wrong. Okay, that whole number's still there. It just has to estimate it to fit it all within the window. Okay, now we've got that done. I'm going to go ahead and find the line for this one. So I'm going to go Stat, Calc, Linear Regression. Okay, I'm going to store it in my Y1, just like we've been doing. Bars, Y1, calculate. Okay, so my linear regression line for this is y equals 2.61 approximately plus 177.19. Okay, now it's stored in my Y1, it's right there. If I hit zoom stat, you see that these points right here are pretty dang close to this line, right? So looks like it's got a little off right there, but not very much at all, right? This line is very close to all these points. This is a great approximation here, okay? It's not exact, but it is an awesome approximation, okay? So this line does a very good job. Simple as that. Now all you have to do is record that line. Now what I will tell you is when you type it in your Y1, it goes pretty crazy with how many digits it actually estimates it to. So coming to your Y1 and actually trying to rewrite your equation can sometimes be hard. Sometimes it's easier just to go all the way back out. So if you wanted to transcribe this, go all the way back out, go stat, calc, linear regression, and just go ahead and recalculate it. You don't have to store it in your Y1 because it's already there. If you recalculate it, you can see your estimation here a lot better. So I'm going to go over to your page, write it down, and move on to the next example. Alright, so here it is. So we did all this. We did the scatter plot, aligned everything. We created a linear equation that is the best fit line for these data. It was y equals 2.61x plus 177.19. Easy enough. Okay. So this one says, in this set of exercises, number 1 says, without graphing, determine which of the following data sets are exactly linear, approximately linear, and nonlinear. So if we look at this one goes up 1, 2, 3, 4, 5. So it goes up consistently. All of them do, which is exactly what we need it to do. Now, the change from 5 to 8, if we find the first differences here, 5 to 8, that's a change of 3. 8 to 11, that's also a change of 3. 11 to 14, that's also a change of 3. And 14 to 17 is also a change of 3. All your first differences are the same. That means that your set is exactly linear. So A is your exactly linear one. Okay. B. Let's look at B. So it still goes up 1, 2, 3, 4, 5, which is good. We need it to be constant. From 2 to 5, that goes up by 3. From 5 to 10, that goes up by 5. From 10 to 5, that goes up by negative 5. And from 5 to 2, that goes up by negative 2. So, oops, negative 3, I mean. 5 to 2, that goes up by negative 3. So, what we see here is that our differences are pretty way different here. So, this one, it almost looks like it goes up and then comes back down. So, it's almost looking like it could be a squared function or quadratic. So, this one would be the nonlinear one. And if you weren't sure about B, you could have gone ahead and done C and compared the two, and then you would see. So if we do C, the difference between 6 and 8 is 2. The difference between 8 and 12 is 4. The difference between 12 and 14 is 2. The difference between 14 and 18 is 4. So while these aren't the exact same, they're pretty close. 2 is pretty close to 4. So this is the one that you could approximate. So this is the approximately linear one here. And there you go for that example. Easy enough. Now if we move on to page 5, number 2 here says World IT Cloud Service revenues from 2009 and projected 2015 are shown in the table. Let's create a scatter plot for the data with y equal to the billions of dollars of revenue and x equal to the number of years after 2000. B says use the scatter plot to determine whether the data can be fit exactly by a linear function. If so, list that function. Okay, so what we're looking at here, obviously, what it wants you to do is the number of years after 2000. So, year 2009 would be year 9. 2010 would be 10, 11, 12, 13, 14, and 15. Alright. So now all we really got to do is go to the calculator, type this in. We can look at the scatter plot, see if it can be exactly fit by a linear function, and if so, find that function. So let's jump over here to the calculator and do it. Alright guys, so I already have it typed in here. Pause and type it in if you need to. If you need a refresher on how to get there, stat, edit. There's your list. Type your list in. Now we can create the scatter plot. That's easy enough. Let's go ahead and create the line for it. So we'll go Stat Calc, scroll down to Linear Regression, and we will store it in Y1 by going to vars, yvars function Y1, and we will calculate it out. So we get a Y equals 9.18 approximately, plus X plus negative 70.57. Now if we look at this, so if we do zoom stat, which you have to do every time to make sure it fits the line, or fits everything within the screen perfectly, what you can see here is that this is not a straight line, right? We wanted to know if it fitted exactly. It does not fit it exactly at all. So what we're seeing here is this definitely more of a curve shape. It looks like a curve would fit it perfectly, actually. So a linear approximation, really not the best solution here. So if we go back and look here, so it says use a scatter plot to determine whether the data can be fit exactly by a linear function. If so, list that function. You can write it cannot, or not linear, however you want to write it, to express that a linear function is not going to work here. We already did find a line to approximate it, but that line did not do a very good job. It's clearly more of a curve than a line. Not linear, especially not exactly linear. Alright, if we look at table number 3, or number 3 in the table below, shows the usual dosage for a certain prescription drug that combats bacterial infections for a person's weight. Okay, so it says, can the data be modeled by an exact, or modeled exactly by a linear function? Explain. Find the function that models the data exactly. If the model is interpreted continuously, what dosage would be recommended for a 209-pound patient? So if we're looking at this here, one, we can see from 88 to 99 is an increase of 11. Okay. From 99 to 110 is an increase of 11. 110 to 121, increase of 11. 121 to 132, increase of 11. I think you kind of get the point. If you follow it through and you look at these, each of these are increasing by 11. So this one increases constantly, which is good. Now let's see if this one does as well. This is an increase of 5. 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 And if you follow the line, they all increase by 5. So, can it be modeled exactly by a linear function? Yes, it can. Why? Because the first differences here are all the same. I'm going to approximate differences. So because our first differences are the same, we can model it exactly. So we need to find the function that models this data exactly. Now we can do it if we wanted to by hand, or we can use the calculator. Pretty much everybody after this point in the class usually opts to use the calculator here. So let's go over to the calculator, we'll find it, and then we will actually use the calculator to solve part C as well. Part C says if the model is interpreted continuously, what dosage would be recommended for a 209-pound patient? So we'll solve that on the calculator as well. Alright, so we're here at the calculator. Remember, starting from the blank screen, you go stat edit, you type 2 list in. There they go. If you need to hit pause and do that, go ahead. Make sure you type them in correctly. Alright, now we're going to go stat calc linear regression. We know a line fits it perfectly, so we should be able to find the perfect line for this. I'm going to store it in my Y1. Okay, and then I'm going to calculate it. So that what we get here is y equals 0.45 repeating x plus b. So if I go over here, hit zoom, hit stat, you can see the line goes perfectly through all those points. Now, part C said if the model is interpreted continuously, which dosage would be recommended for a 209-pound patient? Okay, so there's two ways you could do this. Okay, patient weighs 209 pounds. Remember, 209 is going to be your x here. Okay, so your x is 209. So I can do the very simple thing of second calc value 209, hit enter, and it finds it for me. X is 209, your y is 95. Okay. If you wanted to do something different, you could sometimes search through the table and find it, but then you gotta hope that this value over here is right. You have to scroll all the way down to x equals 209. To me, that's way too complicated. The easiest way, you can do whatever other method you want to, but to me, the easiest way is second calc value. Type in that x value of 209, and you find that your answer is 95. Okay, so let's go back to the paper. We're going to write the formula down, and we're going to write the answer for C down, which is 95. Alright, so we're right back at it. Find the function that models that exactly. Be 0.45. If you want to take you a little, be a little special here and write the little repeat sign over 45, be my guest. I'm just going to estimate it here. And so the equation is y equals 0.45x. If the model is interpreted continuously, what dosage would be recommended for a 209-pound patient? It would be 95. It's probably a good idea here to put units if they give it to you. It's milligrams. Especially those of y'all going into a nursing or medical field. It's good to know the units for something. Don't want to give them 95 grams if you were only supposed to give them 95 milligrams. You could kill somebody. Alright. On to page 6 and number 4, it says, as the following table shows, projections indicate that the percent of U.S. adults with diabetes could dramatically increase. Find a linear model that fits the data in the table with x equal to the number of years after 2010. Use this model to predict the percent of U.S. adults with diabetes in 2027. And graphically find what year this model predicts the percent to be 31.3%. Okay, so we're looking at years after 2010. Okay, a lot of times the hardest part of this is aligning. So years after 2010 means 2010 is year 0. This will be year 5, 10, 15, 20, 25, 30, 35, and 40. Okay, easy enough. So we've aligned it. Really, all we need to do is type it in the calculator, find the model, and then use that model to predict the percent of U.S. adults with diabetes in 2027, and to find the year where the percent is going to be 31.3%. So we can do that. So let's go over to the calculator real quick. Alright, so we're over here at the calculator. I've already got my list typed in. If you need to pause and type your list in, please go ahead and do that. Okay, so I'm going to hit stat, calc, linear regression. Okay, I'm going to go ahead and store it in y1, vars, y-vars, function y1, calculate. Okay, so I have the linear equation here. Okay, if you want to go ahead and write it on your paper, you can, or you can wait to the very end like I'll do. So, if you want to look at the graph, we'll go zoom, stat. You have to do that every time to make sure it fits it for the appropriate set of data that you've inputted. Okay, it does a pretty good job here. Gets really, really close to all the points. Okay, remember the next question, what it wanted you to find was to predict the percent of U.S. adults with diabetes in 2027. Okay, so 2027, you can't just type in 2027 for x. What you're going to have to do, you can still do second calc value. Okay, the 2027 is how many years after 2010? It's 17 years after 2010. That's what you have to type in. So you don't necessarily type in the year they give you. You have to figure out how many years after that year that you started with that year is. So 2027 is 17 years after 2010. We have to use the 17. Okay, I'm going to round to 2 decimal places here. I'm going to say it's 24.59%, and we'll write that down as well over there on your notes. So the next part, it asks you, was that C part. If you're looking on your paper now, it's easier for you to read than me. It says graphically find what year this model predicts the percent to be 31.3%. Okay, so we need to find when it's 31.3%. Now, usually if they give you the Y value that you need to find, a lot of the times, most of the times, what you can do is go second table, okay, and you can scroll over here and find it. They wanted us to find, it says 31.3%. So what you'll see here is it's somewhere between year 31 and 32. Doesn't give it to you exactly, but it's somewhere in between there. Okay. If you want to be really more precise and find the exact number, if you hit the graph button here, best way I can tell you to do it, 31.3%. Type that into your Y2. Okay. Hit graph. Wherever these two lines intersect at is going to be where going to essentially be your answer. So first curve, second curve, guess where they intersect at? They intersect somewhere over here. Find it for you. It tells you that they intersect in year 31.42. If we round it to the nearest year, it'd be year 31. Okay. So what we're going to need to do is we're going to need to take that year 31 and we're going to need to go over and add that to the initial year, which was 2010, to get the actual year that we're going to look at. So let's go back over to the paper and kind of put it all together in the answers. Alright, so find a linear model that fits the data in the table. So I believe what we pulled up for it was y equals, let's see if I can remember what we had. It was y equals 0.46 approximately x. So y equals 0.46x. And then the v, I believe, was 16.7 approximately. Okay, so there's our equation. We found the linear model approximately. Okay, we used that to predict it with the calculator and came up with that 24.59% for year 2027. Graphically find which year the model predicts the percent to be 31.3%. What we found for it was year 31.43. Okay, we need to round that down because this 4 here tells us to round it down. I rounded to year 31. Okay, and we're looking at years past 2010. Means what I need to do essentially is take this 2010, add 31 to it, and that'll actually be the year in which it occurred. Okay, so if you just give the 31 answer, the 31.43 answer, you're not going to get it right. You need to add it to that initial year. If you do that, you'll see that it's year 2041. So in year 2041, that's when the percent turns out to be 31.3%. Easy enough. Alright, if we look at number 5, it says the table gives the projections of the population in millions of U.S. residents over age 16 for selected years from 2015 to 2060. Graph the data with y equal to the population in millions and x equal to the number of years after 2010. So we're going to have to adjust this one to 2010. Okay. B says find a linear function that models the data. C says what does this model predict the population will be in 2042. And D says in what year does the model predict the population will be 336.827 million. Okay, and it gives us this list here. Okay, so obviously what we're going to do, we have to adjust it for the year 2010, if I'm remembering correctly. So we'll do that first, and then we'll go over to the calculator, type it all in, and we will find all the answers to the subsequent questions. So adjusted to 2010 means we start with year 5. 2020 will be year 10. This will be 15. This will be 30. So that would actually be a 20. And 25. Okay. That'll be a 30 because it's 40. This will be a 35. This will be a 40, 45, and 50. Now we'll take this newly adjusted list and we'll go type it in on the TI. So I'll see you over there. Alright, so we're over here at your calculator. I already have my list typed in. If you need to pause and type your list in, go ahead and do that. So I'm going to go ahead and calculate the linear regression here. So just like we've been doing, still going to save it in your Y1. You should really be starting to become a pro at this. Got to calculate it out. Here's your equation. Y equals 1.89x plus 247.9942. Okay, so that's stored in our Y1. I'm going to graph it all and look at it together. Make sure you do your zoom stat. There it goes. It's not a perfect fit, but it's dang close. Alright, now you know that we have to write the equation for part B. So we've already found the equation. That's no problem. C said, what does the model predict the population will be in 2020 or 2042? So remember with this one, this was years after 2010. So 2042 minus 2010 would be year 32. So that 32 is going to be what you need to use when you go second calc value. Okay, so we'll type in 32 and we find that our value here is 308.47595. Okay, and if you want to approximate that, you can. Typically what will happen when you have to do this for a test or a quiz, it'll tell you how many to approximate it with. It should do the same for your homework as well. Okay, so our answer there is 308.47595. And we'll go write that on your lecture notes here in just a bit. Alright, last question says, in what year does the model predict the population will be 336.827? So, that's a pretty specific number. So, a lot of times when they give you a really specific number, you can kind of scroll in here and find it. Okay, we don't really need this Y2. I'm going to clear it out. It's just distracting me at this point. So, the number we're looking for here, 336.827, I'd say that that's it right there. 336.83, probably just went ahead and approximated it. It's exactly what it looks like it did. So I'm going to say in year 47. Okay. Now if you wanted to find that differently, you could. All I did was scroll and found it in my Y. If you can't find it in your Y, or if you can't find one close enough to it in your Y to approximate your X, then what you might need to do is hit graph, and then what we're going to do is come over here to Y equals. In your Y2, we will put that 336.827, I believe, and we'll graph it, and just like we did before, we'll do second calc, intersect, and where the two values intersect at will be your answer. So this line, that line, scroll it on over to where they intersect at, pretty close to it, and it finds it for you. So just like we said, year 47. Okay, so that would be your answer for that. But remember, a lot of times what it wants you to do, it doesn't want 47 as the answer, it wants you to adjust. So let's go back over to the worksheet and adjust. Alright, so this equation here is the answer for B. So y equals 1.89x plus 248 approximately. Okay. What does the model predict the population will be in 2042? We found that to be 308.48. That is in millions, so you might want to write your unit. It's always a good idea to keep track of your unit. Okay. Alright. D says, in what year does the model predict the population will be? 336.827 million. Okay. So 47 is probably not the answer they're actually going to be looking for. They're going to want to find the actual year. It's years after 2010, so we need to take 2010. We need to add 47 to that. Okay. Add 47 to that. You should find that it's obviously year 2057. That would be the answer that we're looking for. So if you give this, you're probably going to get it wrong. The answer you need to give is that one, 2057. Now, if we move on along, I think question 6 is the last question of this lecture. So let's look at question 6 here. Question 6 says the table shows the national expenditures for healthcare in billions in the United States for selected years from 1995 with projections to 2020. Find a linear function that models the data with x equal to the number of years after 1990 and y equal to expenditures for healthcare in billions of dollars. Okay. B says, what does this model predict the expenditure will be in 2019? During what year does the model predict expenditures for healthcare will be 4,659 billion? Okay. The cool thing is we've done so many examples this class period that you should really be able to do this one almost with your eyes closed if you know where the buttons are at. That being said, I'm going to leave one for you to do. I expect you to do this one on your own. If you have any problems whatsoever, please email me about it, okay? You should be able to do this one, knock it out, no problem. If you're one of those persons that's really nervous about your answers and want to make sure you got your answers right, hey, that's a good chance to reach out and email me, right? We're supposed to have some kind of contact here. I'm supposed to know that you're actually paying attention and going along, so email me if you have troubles with this. If you don't have troubles, let it ride, okay? Know what you're doing, let it ride. You know how to do it, just finish filling out your lecture notes here, and you're done. All you're really doing is typing it in the thing, letting the calculator do all the work for you. It's not that hard. It's not that many to type in. I don't feel like you need to watch me at this point. But if you do struggle with it, come to my online office hours, send me an email, ask me about it. Fair enough. All right. If you need any help, let me know. Otherwise, I will see you in the next lecture.